Hello, ladies and gentlemen. Welcome to section 4.2, which is entitled Using Newton's Second Law. And Newton's second law is F equals ma. That's force is equal to mass times acceleration. And it's the most important equation you're going to get in the first semester. F equals ma. It's so important that this guy tattooed it on his arms. Right along Mr. Einstein and his equation E equals mc squared. In the back of my room, I have a book entitled Science Inc. It's in my little library that's over there. If you want to see other cool tattoos that people have done that are very science-y, go ahead and check that out. But down below, I have if you're a Zelda player, it's the Master Sword. And sometimes I like to refer to Newton's second law, F equals ma, as the Master Sword. And I also like to put this little net down here. The net force causes acceleration. And here's the sentence that I want to work around today. If you have a net force acting on an object, then the object accelerates in the direction of the net force. This is a huge, huge, huge statement. If you have a net force that's acting on an object, then the object accelerates in the direction of that net force. And I can say this a different way too. I can say if you have acceleration, I'm going to switch it around. You have acceleration on an object, then the object has a net force. See what I did? I switched these around. Acting in the direction of the acceleration. I can also say this. If you have no acceleration on an object, then the object has no net force in the direction of the acceleration. And I can even go back and say it one more way. That was the inverse, by the way. When I switched the first and the second, they call that the inverse. And if I do the negative inverse, I think that's called like the converse, and then it's a bunch of weird discrete mathematics stuff. But I can also say if I have no net force acting on an object, then the object does not accelerate. So this is huge. You can use no, you can switch it around, and that helps me identify which force is bigger when I have lots of forces acting on an object, because I look for the acceleration. If it's accelerating, then there's a net force. One of the forces is bigger than the other. If there's no acceleration, then the forces have to cancel each other out. It's as simple as that. And the first thing I have to kind of illustrate this point, this is my buddy Felix Baumgartner. He's an Australian dude, and he jumped out of a helium balloon 2 years ago, no kidding, from a height of 128,000 feet. I don't know if that means anything to you, but commercial airliners fly at 30,000 feet. I mean, and that right there is 6 miles. And this is 4 times that. So this guy was, no joke, 24 miles in the air. It was an incredible logistical, tactical, scientific thing to overcome and do that, but it's really, really cool. So here's Felix above the earth. And as he's falling, there are forces acting on him. The first and most prevalent force is gravity. Let's say Felix, as he falls a little bit further, gravity is still there. And then you have Felix after he pulls his parachute. that same force of gravity is still there. But now you've got air resistance. Is air resistance bigger than, smaller than, or equal to gravity? And the answer to that is he accelerating? At the very beginning, he's accelerating downwards. When he reaches this, it's called terminal velocity, he's not accelerating. And then he slows down. That acceleration tells me everything I need to know about air resistance. At the beginning, the air resistance is very small. See how the downward amount of gravity is bigger than air resistance? That gives you an acceleration down. There's a net force pointing down. That means that there's acceleration. I go back to my master sword. If you've got acceleration acting on an object, then you have a net force. I just switched these around. I have to have a net force to have acceleration. Right here in the middle, he's cruising at a constant speed. That means air resistance is the same amount. And this is called terminal velocity. That's when your air resistance reaches and equals the force of gravity. So this air resistance is going to start getting bigger and bigger and bigger the faster and faster he goes until he reaches terminal velocity, and at which point he's going to pull his parachute, and now air resistance is a lot bigger than gravity. That's what slows him down. So he can land at a comfortable speed and not break his legs. So this Master Sword, you just saw how I used it to figure out is the relative sizes of the forces involved. Gravity is the same no matter where. It gets a little bit deeper than that. I mean, the farther away you go from Earth, the less gravity there is, but it's not that big of a difference. So this gravitational force is the same everywhere. But air resistance changes, and all I do is I look at the acceleration in each case, and that will tell me which one's bigger. For instance, let's look at this one, this scenario right here. This is an example problem I pulled right from your book. I've got Anuja and I have Sarah both pulling on dogs. Sarah here is pulling with a force of 10 newtons to the left. Anuja is pulling this way. Notice I made it a little bit bigger because her force is 11 newtons. So my net force is 1 newton to the right. So if I wanted to figure out what is the horizontal acceleration, I'm going to use this, Newton's second law. And again, I like to use the net in here because the net force, first of all, maybe I want to say that positive is this direction. So that means that I have my force of Anuja minus the force of Sarah because Sarah is pulling in the negative direction. Anuja is in the positive. That's why this is positive, and that's why this is negative. Sarah, the mass, and the acceleration. I know that Anuja is 11, and I know that Sarah is 10. I know that the mass is 0.30, and I can figure out the acceleration. 1 divided by 0.3, I get 3.3 meters per second squared to the right. It's a positive number. So I used the fact that I know that one's pulling more, so that means it accelerates to the right. It accelerates, not at a constant speed, it's accelerating. Mass and weight. Here I got a person standing on a scale, and it says the upward force of the spring in the scale is equal to your weight when you step on it. So here's a person, and they're standing on a scale. This person weighs a certain amount, and there's an upward force provided by gravity, or I'm sorry, the Earth pushing up. That's called the normal force. Now, what the scale is going to read whatever the normal force is. So for instance, like let's say you're on the giant drop, and this thing all of a sudden goes away, the normal supporting force, you go woof, accelerating down, your scale's going to read 0. Then at the bottom of the giant drop, you slow down, which means that you're accelerating in this way. It comes to a screeching halt. That means that this normal force gets really big. And now your scale is going to read something really huge. But mass and weight, first of all. Mass and weight, it's just F equals ma. You take your mass, which is in kilograms, and you put it into here, and then you multiply the acceleration, and the acceleration is always going to be 9.80 on planet Earth. So if you know what your mass is, you multiply it by 9.8, and you end up getting the weight. The weight's going to be in newtons. And you'll see that in just a second. I'll do this last example problem. So here, I've got an example problem where I've got you, and you are 75 kilograms. And you're standing on a bathroom scale. And you are accelerating up at 2.0 meters per second squared. So here I am accelerating. And then I move at a constant speed where my acceleration is 0 for some unknown time. I know that the time in the first point is 2 seconds. Okay, and then I continue at constant speed. Is the scale reading during the acceleration greater than, equal to, or less than the scale reading when it's at rest? So when I'm at rest, here I am, my force of gravity. In order for me to accelerate upwards, this has to be bigger. It has to be bigger. That's the only way I can get acceleration, referring back to that master sword. If I have acceleration, I move the acceleration up, acting on an object, then the object has a net force in the direction of the acceleration. I'm just switching the words around, but it remains true. So the answer to this question is greater than. It's greater than. Now, what if the question had asked, what does the scale read during this constant velocity period? Well, when my acceleration is 0, that means my net force is 0. Going back to that master sword. If I have no acceleration, that means I have no net force. So that means that the normal force is equal to gravity. Now, one more extension of this exact same problem. What if the problem had said, what does the scale actually read? I wonder what this scale actually reads. You could do a couple of things. First of all, I got to figure out what my weight is. And remember, to figure out what my weight is, I use F equals ma. I know that my mass is 75 kilograms, and I know that the acceleration is 9.80. So if I take 75.0, by the way, times 9.8, I get 735 newtons. That's how much I weigh. So here's why I go and I use Newton's second law again. Now, I want to say that up is positive, just to kind of help me out here. I have two competing forces. I've got an up force and I've got a down force, right? My up force is positive because I just said it was I just created up as positive. My normal force minus my force of gravity is equal to the mass times the acceleration. I don't know the normal force, but I know gravity is 735. I know that the mass is 75, and I also know that the acceleration is 2. So 75 times 2 is $1.50. So then I add 735 to that, and I get 885. So this normal force over here is 885. And that makes sense. In order for me to accelerate upwards, I have to have a bigger force upwards. The scale is going to read above by 150, that's where the 885 came from. So just a quick recap. F equals ma is it is the most important. It's probably the simplest, but it's also the most conceptually complex. I mean, it's so complex, but it's so simple. It's just F equals ma. It states that, if you have a net force acting on an object, then the object will accelerate in the direction of that net force. And we can modify those words. The forces are relative. Like, depends, is there acceleration? Are you accelerating down? No acceleration? Or accelerating up? That's the key for me when I look at any problem. Am I accelerating? If you have a net force, Anuja is beating Sarah. Net force causes acceleration. And we can use Newton's second law to figure that out. Mass and weight. Remember, you take your mass, which is in kilograms, multiply by 9.80, and you get weight, which is in newtons. And then lastly, can you apply this with my mass and weight over here in red, trying to figure out what the mass and what the weight is, and then using Newton's second law again to figure out how big that force is when you're accelerating upwards.